Greetings. Let's continue our discussion on the electron gas and the Hartree-Fock approximation, which we started recapitulating in our previous class, which was of course a different approach to the Hartree-Fock self-consistent field than what we did in our previous course on atomic physics. So this was a slight variant of that approach. And specifically this approach is geared toward introducing the random phase approximation, in particular the Bohm-Pines formalism of the random phase approximation, and that is what I hope to get into in the next couple of classes. So today our focus will be on the treatment of the kinetic energy part and the exchange energy part which is involved in the electron gas interactions. So we wrote the Hartree-Fock self-consistent field equation, which is a condition which must be satisfied so that you get a self-consistent field according to the variation principle, and this relationship we arrived at in our previous class. So this would be an appropriate point to begin discussion for today. So you have got the kinetic energy term and then the exchange term. Notice that epsilon is used twice in this equation. One is in the second term on the right hand side, on the left hand side, second term on the left hand side, which is the exchange term, and epsilon is also used on the right hand side, but on the left hand side you have got k as a subscript, whereas on the right hand side you have got k as an argument, and these two stand for different things. So epsilon subscript k on the left hand side is the exchange term, and epsilon argument k is the term that you get from the Lagrange multiplier in the Hartree-Fock formalism. So that is something to be kept track of. And we also found in our previous class the complete expression for the exchange term, which is minus 4 pi square over L cube, and you must sum over all the states, and you have got 1 over the modulus square of the difference between k and k prime when you sum over all the states k prime. Now this is the subscript k corresponding to the exchange term and the argument which comes from the Lagrange multiplier term in the Hartree-Fock formalism. So just remember that, so there is no reason to get confused by the two epsilons which appear in this. So essentially you have got the Ek plus the kinetic energy part plus the exchange part, which give you the Hartree-Fock energy for the electron gas and the Gellium potential. Of course we have already made some approximation. This is an electron gas, and the positive nuclear charge which is there in the metal is smeared over the entire region of the metal of the whole area. It takes the whole expanse with a uniform charge density. So that is the Gellium potential which we are making use of. Now we have to determine the kinetic energy part and also the exchange part. So let us focus on the kinetic energy part, for which the k appears as a subscript. Now this is the model that we have. You got a positive charge. The entire positive charge at all the lattice sites is smeared over the entire region of this metal, and the charge density is uniform. It is the number of electrons times the electron charge divided by the total volume. So that is the average charge density. The volume of the box, let us say, is L cube, each side being of length L. What we have done, and this is with reference to the discussion in the previous class, we have done a box normalization of the free particle free electron waves. So that is the kind of normalization we have done. We estimated the number of wavelengths that will fit in a box, and we get a quantization condition. So this is the discretization of the continuum in a certain sense, and that gives us a condition on the wave vector, and essentially what you find that you can talk about an average volume for each state, because you get from one state to the next by changing the integer quantum numbers, and the average volume for each state will be the cube of 2 pi over L, as you can see quite clearly from this. So this is the term that we want to work with. We have found that the volume of each state is the cube of 2 pi over L, but we are dealing with a sum over all the states. But when we go to a continuum model, because the electron wave vector, when you take the free particle states, which is what we are using, e to the I k dot r type of solutions for free particle states, then of course you need to carry out integration over all the states rather than summation over the discrete states. So you have to change over from this discrete summation to integration. So this will be an integration over all the states, and you must integrate over the entire volume and divide it by the average volume of each state, which is 2 pi over L whole cube, right. So that is what the summation k prime will be replaced by. So let us go ahead and do this integration now. So what you have as a summation here effectively becomes, you have the same term minus 4 pi e square over L cube over here, and instead of this discrete sum you now have the corresponding equivalent integration. Okay, how this is integration in the k space, but it is not over all the values of k, because in the ground state the uppermost k level which is filled is the one which is at the Fermi level, right. So you have to carry out the integration only up to the Fermi level. So if the Fermi level corresponds to a momentum in units of h cross, which is given by kf, then integration over the variable k prime will go from 0 through kf, and then in the spherical polar coordinate system in the momentum space you will have theta going from 0 to pi and phi going from 0 to 2 pi, and then of course you have the modulus square of this difference vector, which is k minus k prime, which I have written as a dot product between this vector with itself. So this is the integration that we have to carry out, which I bring to the top of this slide now, and I transfer the variable explicitly from k to p, and the difference is only this h cross. So that tells us that the differential increment dk is dp over h cross. So you make corresponding changes over here and write this integration over the momentum from 0 to the momentum at the Fermi level, and then of course the rest of the variables are appropriately adjusted, scaled by the factor h cross, right. So let us carry out this integration in the momentum space over the variable p. Now here the integration over the phi variable, because there is nothing that will depend on phi, so this will give you a factor of 2 pi over here, then you are left with integration over theta and p, and as you would have done in a large number of exercises, it is very easy to carry out this integration by changing the variable, put mu equal to cos theta, and then change the integration over theta to that over cosine theta, which is over mu, and that gives you this integral. Okay. So now you have integration over mu going from minus 1 to plus 1. There is a minus sign here which takes care of the cosine theta correctly, and we will now work with this integral. You have to integrate over mu going from minus 1 to plus 1. Make sure that you have the correct signs, and what do you get? So you have the integration over cosine theta, which is to be done first, followed by integration over momentum going from 0 to the Fermi momentum, to be done next. Okay? So, now this is a straightforward integral to be done. You get a logarithmic term and then you have to put the limits -1 and +1, right. So, you get the upper term and the lower term which you must subtract. For mu equal to -1 will be the lower term and mu equal to +1 will be the upper term, right. So, this is integration over cos theta, which is integration over mu. So, you have a minus sign here and a minus sign here. So, you can drop both of them and now you have a rather simple expression, but you have to put these limits. Okay? And after putting these limits, then you have to carry out the integration over the momentum. Now, this is fairly straightforward mathematics, but I will take you through some of these steps. So, this is what we have got in our effort to get an estimate of the exchange term. So, now let us put the limits. Mu equal to +1 will give you the logarithm of p square plus p prime square minus 2 into p prime with mu equal to +1. So, that is the first term that you get, and from this you subtract the second term corresponding to mu equal to -1, which multiplies this -1 and gives you a plus sign over here. So, this is what you get after the integration over mu or cos theta has been completed. Now, notice that there is a p prime square here and you have got a p prime in the denominator. So, one of these powers can be reduced and you simplify this expression a little bit. Having reduced one of the powers, you get p prime over p. This p is coming from this common p in the denominator in both the terms. So, we have this integration over p prime going from 0 to the Fermi momentum, and then you have got this logarithmic term, and you can play with this logarithmic term a little bit and write it in this form. These are straightforward substitution. You have got logarithm of the modulus square, so you get a 2 log over of that ratio, and you can strike out the factor 2 now, and then without the 2 you have the rest of the term, and that is what gives you the expression for the exchange term as this. Okay? All right, we can simplify this further because we want to bring it into a form which is one of the standard forms for integration. So, now we have it as a difference of two integrals, and we use this standard form of the integration for x log x plus a, which is a well known integral formula. So, we use this in the above expression, and that gives us a number of terms over here. So, we get similar to this x square minus a square by 2 log x plus a, we get this term over here, and then for this x minus a whole square over 4 we get p prime plus p whole square over 4 from this term, and likewise we get 2 terms from this. Okay? Now, you do not have to write this down very quickly because you will have access to the PDF file in which all these formulae are available. Okay? So, they will be uploaded at the course website, but you need to follow how the derivation is being done. Okay. So, now you have to put the limits because you have an upper limit p prime equal to the Fermi momentum and the lower limit is p prime equal to 0. So, you have to write this expression for the upper limit and subtract from it the corresponding expression for the lower limit. So, let us do that. So, we have the upper limits and the lower limits to be respectively the Fermi momentum and 0. So, we get this expression with p prime equal to the Fermi momentum. So, you instead of p prime square minus p square, you get pf square minus p square and the corresponding terms with pf Fermi momentum over here, and you have the same expression for the p prime equal to 0. But notice that this term simply vanishes. So, there is nothing that is left of it, and now you have only the upper expression which you have to be working with. Okay. So, now you have an expression for the exchange term, which is in terms of this Fermi momentum. This will depend on the value of the Fermi momentum. This you can simplify because there are common terms over here. You get minus twice p into pf, and from both of these terms, so you get minus 4 into p into pf, which you divide by 4, so you get p into pf, and the other terms will cancel each other because there is a minus sign here and a plus sign here. So, the only thing that is left from these terms, the last two terms, is this minus pf into p. Okay. So, this is a little bit of further simplification. This minus p into pf has been factored out as a common between the two terms inside this rectangular bracket. So, you get plus 1 over here, and you have a minus sign sticking out over here, and then you have this p into pf in the denominator, which takes care of the factorization. And this is the exchange term as we have got. Okay. Now, here this is the expression that we got from the Hartree-Fock equation. This is the kinetic energy part and this is the exchange part. We found out after substituting this term over here, we have this general form, and it is very often customary to write this in terms of the ratio rho, which is the Fermi momentum over the momentum variable p, which simplifies this or enables you to write this term in an equivalent form. So, there is nothing new with this except that it is being written in terms of the ratio rather than p and pf. Okay. So, you get rho square minus rho over here, and here inside you will get 1 plus rho and 1 minus rho. Now, pf over h cross gives you the kf. So, that is all there is to it, rest of the terms being the same. And it is often you will find in some of the literature, especially in the books by Reims or the articles by Bohm, that he writes this factor inside this box as f of rho, because then it becomes simple to write, and one can even examine the behavior of f as a function of rho. So, this is the result that we have got. Keep track of the sign. You had a plus sign here and a minus sign here, which essentially means that the exchange term has got this minus sign. Rho is pf over p, but the variable p is always less than the Fermi momentum, because all the electron states are occupied only up to the Fermi level. So, by definition this p is always less than pf, which means that rho is always greater than or equal to 1. Okay. So, rho being always greater than or equal to 1, rho square minus 1 will always be positive, and it is you can see that the exchange term will be essentially negative. So, it reduces the energy with reference to the kinetic energy term. Okay. It does not add to that energy, it actually reduces it. Now, this is a result that we have actually met before, because when we did the previous course on atomic physics, we discussed the singlet and the triplet states, and we quoted from Landau and Lifshitz that the triplet state is less punished by the Coulomb interaction, because you have this exchange interaction, and in the triplet state for a 2 electron geminal wave function always has a lower energy than the singlet state. So it is the same kind of result, and let me remind you of this result a little bit, because the singlet wave function has got an antisymmetric spin part and the orbital part is symmetric. Okay, so this is the singlet state, and as you can see from this, what happens that as R1 tends to R2, as these two arguments get close to each other, the first term and the second term would add and double each other, right. So it is like, you know, you will have a doubling of that wave density, and you will be stacking the charges together. So you generate a heap of electrons. This is actually called as a Fermi heap, and what it will do is that in this heap the electrons, the two electrons will get closer to each other, and as a result of that there will be increased repulsion, okay, because the closer they get, the force of repulsion goes as, you know, 1 over r square. So there will be increased repulsion, and that will make this state less stable. So that is the reason it has got higher energy, and correspondingly if you look at the triplet state, you have got an antisymmetric space part. So you have got the argument R1 and R2 in this geminal wave function, and what will happen as R2 tends to R1, then you will have the orbital part practically vanish, and that is part of the reason that the triplet state, if it has to exist, will tend to keep the particles separated, and once they are separated, that will reduce the repulsion between them, and that will stabilize that particular state. So you have essentially the exclusion principle and the antisymmetry of the wave function, which is influencing these dynamics. So it is as if there is a cavity around each electron which prevents any other electron from with the same spin enter that space. Okay, so that cavity is called as a Fermi hole. So as opposed to a Fermi heap of the previous case, you now have a Fermi hole. So these terms are sometimes used, and you have it is called as a Fermi hole. It is also called as an exchange hole, and what it does is it reduces the repulsion and it stabilizes the state. I will now refer to the Hartree-Fock equation, which I recapitulate from the previous class, which was on slide number 54 of the previous class. This is the Hartree-Fock equation for the free electron gas. This is very similar to the Hartree-Fock equation that you have in atomic physics, with the difference that the term over here was the nuclear attraction between an electron and the nuclear attractive potential. In this case, this is the Gellium potential. In the present case, this is the free electron gas in a Gellium potential. So this is not an atom we are working with. So the relationship is similar, but of course there are important differences which we have to keep track of. You have got a Gellium potential, and as we discussed in the previous class, the electron Coulomb repulsion, which is the direct interaction term. Now this direct interaction term, and then you have got an exchange term. So these are the two terms which are similar to what we have in the atomic case as well, but in the present case these two terms, which is the Gellium attractive potential term and the electron repulsion term, they are exactly equal and opposite. This one is attractive, this one is repulsive, and they are exactly the same, so they will cancel each other. Okay? So the Hartree-Fock equation for a free electron gas is now left with only this kinetic energy term and this exchange term. Okay? These two happily cancel each other. So these are the two terms. This is the kinetic energy part and this is the exchange part. So this is now the Hartree-Fock equation as we have, and we have already seen that in the momentum space, now let us try to get some numbers for the exchange term, for the kinetic energy term and the exchange term. So, because eventually we will have to do some calculations for these. So, we already know that the discrete summation is equivalent to this integration over the momentum space up to the Fermi momentum divided by the average volume of each state. In the momentum space, of course, there is an extra factor of h cross, right. So, the momentum summation over p prime will give you a corresponding term over here. So, we are now going over to integration over momentum space rather than integration over the k space. They are linear with a factor of h cross, and we will get an expression for the Hartree-Fock in the for the electron free electron gas in the Gellium potential by simply looking at the comparison between the corresponding expression for the atom, which we have done in considerable detail in the unit 4 of our previous course, and these are the references which are available to you. So, this whole lecture is available at this link, and the corresponding PDF files are also there. So, this is the expression for the Hartree-Fock in the atomic case, but now we have some differences here, because this term, which was the single particle operator in the atomic case, which consisted of the kinetic energy operator and the nuclear attraction. Now, we do not have that. Instead of that, we have the Gellium potential, right. So, we are going to have an electron gas and a Gellium potential. So, the one electron part will be somewhat different, it has to be modified, and we will simply borrow this result and adapt it to the electron gas in the Gellium potential by making corresponding changes. So, we have first of all the electron gas and a Gellium potential, and we also know that this term, which is coming from the Coulomb term, right. This would go, because this is the one which cancelled the electron direct Coulomb repulsion term. This would cancel the attractive Gellium potential, as we have seen, as we have discussed, right. So, these are the two changes that we shall remember, and therefore, all we have to do is to replace the summation over these discrete states by integration over continuum states going up to the Fermi momentum. Now, once we make these changes, we can straight away adapt to this result of the previous course from unit 4 and write this expression for the energy, for the Hartree-Fock energy, not for the atom, but for the electron gas in the Gellium potential. So, now you have this integration over the momentum space. You have got in this the kinetic energy term, which is here, which is P dot P over 2m, right. You do not have this term anymore, because this is the one which has cancelled the Gellium potential, but you do have the exchange term, which is here. Okay. So, this is straight away a direct adaptation of the Hartree-Fock result of the previous course. So, instead of spending extra time and re-deriving this expression, I chose to adapt this relation for the electron gas, for the free electron gas. So, here we are, this is what we have got. This is the Hartree-Fock energy for the electron gas and the Gellium potential, and this is now a sum of these two terms, the kinetic energy part, which is coming from here, the P dot P over 2m, the P square over 2m, and then you have got the exchange term. So, this is the kinetic energy part, which I have now written the two integrals separately, Ek, the first one which is with a subscript k for kinetic energy part, and the second is the exchange correlation term, and these are the two integrals that we have to work with. So, let us have a look at this. Here you just have an integration over the solid angle, okay, which will give you a factor of 4 pi. And you have p square and then p square over here. So, you will end up integrating a 4th power of p. So, that gives you p to the 5th, at the Fermi momentum over 5, and this is the expression for the kinetic energy term. You get h cross square after simplification of all the terms. You have got 2 pi h cross to the power 3, and then you had p to the power 5. So there was an h cross to the power 5 sitting over here. So that is what leaves you with h cross to the power 2. So when you take care of all of these terms, this is what you get for the kinetic energy part. Now the subscript f, of course, is the Fermi level, corresponds to the k value at the Fermi level, and L cube is the volume of the box, which is what I have written here. This result is straight from the book by Reims, which I strongly recommend for this part of the course. Okay, so this is, let's try to estimate what it will amount to. This is in the K space. We already know that the volume of each state is the cube of 2 pi over L. The total number of electrons is n, and since there is one electron per state, there are those many states that we have to work with. So this will be twice the number of single electron states in the volume spanned by the Fermi sphere, and this volume is 4 by 3 pi k cube, right. So this is twice this number. So you have twice 4 by 3 pi k cube, which is this Fermi sphere, divided by the volume of each state, which is 2 pi over L whole cube, and then you can rearrange these terms, do a little bit of simplification, okay, which is quite straightforward, and you find that this n turns out to be given by the cube of this k, and k turns out to be the 1/3 power of n over v, which is the density. Okay. So this is what we have got. These are the two forms that we get. We have, if you now consider Rs, R subscript S, to be the radius of a sphere whose volume is equal to the average volume per electron, just have some variable for that, which is the average volume that you have per electron. So this average volume multiplied by the total number of electrons will give you the total volume, and this we have found out to be what it is. Now that gives you Rs, this radius of a sphere whose volume is equal to the average volume per electron, to be given by this relation, and that tells you that this Rs, you find a mechanism to find what this value of Rs is. What it gives us is the expression for this term Ek in terms of Rs, but this is Ek in terms of the total number of electrons. So it is best that we normalize it for the average Ek per electron. So you divide Ek by n, that gives you an estimate for the kinetic energy contribution to the average Hartree-Fock ground state energy per electron, because you have divided it by the total number of electrons, and that turns out to be this particular value, and all of these are universal constants. So you can find out the corresponding values in appropriate units, okay, and in terms of energy units, it turns out to be 2.21 over Rs square Rydberg, okay, and the Rs itself will be in the Bohr units. Now this gives you a good estimate of the average energy per electron. Now is this really correct? Now we already know that we have to make a correction for the exchange, because this is just the contribution coming from the kinetic energy part, okay. So, when you make a correction for the exchange, you get a better estimate. But then even that is not enough. So, that is what many body theory is about, that is what the random phase approximation is about. So, first of all, we have to make correction for the exchange correlation term, and this exchange correlation, so we already knew that the Hartree-Fock energy is the sum of the kinetic energy part and the exchange correlation part, and we know that the exchange correlation is given by this term. We have this result from our previous analysis. Exchange term, we got an explicit expression for this, okay, and we will use this to get an estimate of the exchange part. So, that will be our subject for discussion in the next class, and what we will find is that when you make an estimate of the exchange term, you do get a better estimate of the average energy per electron. You improve upon it, but even that is not enough, because what we have done in the Hartree-Fock is we have taken care of the kinetic energy part, we have taken care of the exchange interaction, in other words we have taken care of the Fermi-Dirac statistics, but we have still left out something, which is the Coulomb correlations. That is where you will need many body theory, you will need some new and powerful techniques. You can try if it can be done with perturbation theory. It will turn out that perturbation theory is not adequate for that, but we will get an estimate of the correction we get by taking into account this exchange term in our next class, and subsequently we shall proceed to account for the Coulomb correlations which are left out of the Hartree-Fock by following the method of Bohm and Pines technique, which is known as the random phase approximation. So, that is what we will discuss in the next class. So, thank you very much for today.